Lesson 832, Statistical Tests for the Difference in Two Population Proportions. Introduction. In the previous lesson, we began testing hypotheses that compared two population proportions. We learned that when the sample size is large enough, the test statistic, which is a z-score, that's equal to a fraction, or in the numerator we have parentheses p hat 1 minus p hat 2 minus parentheses p1 minus p2, and then divided by, in the denominator, the square root of p bar times 1 minus p bar divided by n1 plus p bar times 1 minus p bar divided by n2. That test statistic has an approximately normal distribution and may be used to test claims regarding the equality of population proportions. Our approach was informal. In this lesson, we will discuss the topic of hypothesis testing in greater detail. Try these. Here in the US, we have been hearing about the effects of global warming, but we are interested in whether there has been any change in people's opinions about global warming. In 2 consecutive years, 2010 and 2011, the Pew Research Center conducted polls to find the proportion of adults in the US who were concerned about the effects of global warming. The results of the 2 consecutive polls seemed to indicate that there had been a change in public opinion over this period of time. Suppose that we decide to test the claim that the proportion of adults in the US who were concerned about the effects of global warming changed between 2010 and 2011. We gather independent samples. In the year 2010, that's the initial year, our data tells us that X sub I equals 233 out of Ni equal to 359 randomly sampled adults were concerned about global warming. The following year, XF equal 194 out of a random sample of NF equal 352 adults were concerned about global warming. Using a 1% significance level, we can now test the claim that the true population proportions are different. First step, determine the hypotheses. When testing for the difference between two population proportions, the null hypothesis states that the population proportions are equal. So just something for us to remember, null hypotheses always have equality. So here H sub 0 for the null hypothesis, and that says P1 equals P2. And we should also remember that means the same thing as the difference P1 minus P2 equals 0. The alternative hypothesis is one of the following inequalities. So HA for alternative hypothesis, we could have P1 less than P2, that's a left-tailed test, P1 greater than P2, that's a right-tailed test, and P1 not equal to P2, that is a two-tailed test. Number 1, for the global warming test, we claimed that the proportions of people concerned about global warming were different for the 2 years under consideration. Let Pi represent the proportion of adults in the US who were concerned about global warming in the initial year. Then let Pf represent the proportion of adults in the US who were concerned about global warming in the following year. Part A, what is the null hypothesis for this test? Again, just right up at the top, right below step 1, we will have that the null hypothesis states that the two proportions are equal. So we simply have H0 for the null hypothesis, which says Pi is equal to Pf. And while we're at it, we can also write down the difference, Pi minus Pf is equal to 0. Part B, what is the alternative hypothesis? Here we should look back at the claim. Under number 1, it says we claimed, and then what's written right after that? The proportions of people concerned about global warming were different. If two things are different, it means that they are not equal to each other. So that means that our alternative hypothesis, HA, says Pi is not equal to Pf. And also while we are here, we can write something down about the difference. Pi minus Pf is not equal to 0. And we can also remind ourselves that this alternative hypothesis, that is our claim. And then part C for number 1, is this a one-tailed or two-tailed test? It says think about the alternative hypothesis. How do you know that this is a one- or two-tailed test? So first of all, we can say that it's two-tailed because we see the not equal to sign. So this is two-tailed since the not equal to symbol is in the alternative hypothesis. And also we can say the word different is in our claim. Step 2. Collect the data. In order to perform a hypothesis test for the difference in two population proportions, we must make sure that the underlying sampling distributions for each sample are approximately normal. We will consider the normality criteria satisfied if there are at least 10 successes and 10 failures in each sample. So this is the same thing that we saw in Module 7, and we've also seen it a few times already in this module. Number 2, for the global warming test, count the number of successes and failures in each sample. In this test, a success is a person who is concerned about the effects of global warming. So part A, for the initial year, how many successes were there? So how many people were concerned about the effects of global warming? If we go back to the details, right below try these on the first page of the lesson, we can see that we have for the first year, the initial year, XI is 233. Those were the number of people concerned about global warming. So 233 successes. And then how we will get the number of failures is taking the total and subtracting the number of successes. So if we take the total for that initial year, 359, and then subtract the number of successes, 233, that's going to give us 126 failures. Same thing for the following year. There we had 194 successes, and then we also had a total of 352 in our sample for that following year. So if we take 352 minus the number of successes, that gives us 158 failures. So then part C, are these successes and failures enough to consider that the approximate normality criteria have been met? Yes, all 4 are greater than 10. The sample proportions, p hat 1, which is equal to x1 over n1, that's successes over total, and p hat 2 equal to x2 over n2, estimate the population proportions p1 and p2 respectively. The difference in the observed sample proportions is p hat 1 minus p hat 2. Number 3, for the global warming test, let's calculate p hat I and p hat F. Again, this is just taking success over total for each. So p hat I would be the successes, 233, divided by the total, which is 359. And if we divide those and round to 3 decimal places, we will get approximately 0.649. And then for p hat F, the successes that we had was 194, and then the total 352. Dividing those and rounding to 3 decimal places, we get 0.551. Part B, calculate the observed difference in sample proportions, p hat I minus p hat F. This is going to be equal to 0.649 minus 0.551, and that gives us 0.098. We're going to need that later. That just summarized a lot of our sample data. Step 3, assess the evidence. we use a sampling distribution of differences between sample proportions to assess the likelihood of the observed difference occurring. As we have seen, the test statistic for the two proportions test is this same z-score that we saw at the early part of this lesson. This test statistic is a z-score for the difference in the observed sample proportions. To find the z-score, we subtract the mean of differences, p1 minus p2, from the observed difference, which was our p hat 1 minus p hat 2. And then we divide by the standard error of differences. The null hypothesis indicates that we should use p1 minus p2 equals 0 for the mean of differences. The formula also requires what we had called the pooled proportion from the previous lesson. That was p bar, which is equal to x1 plus x2, that's the total of the successes from both samples, divided by n1 plus n2. That's the total of the sample sizes from both samples. Number 4, for the global warming test, the pooled proportion is p bar equal to, the numerator says 233 plus 194, and then the denominator says 359 divided by 352, and that fraction is approximately equal to 0.601. With this, the standard error of differences is S with a subscript p hat I minus p hat F. That just stands for standard error of the differences. And then equal to the square root, and we have under the square root 0.601 times 1 minus 0.601 divided by 359. That's p bar times 1 minus p bar divided by n1. And then plus, also still under the square root, the fraction 0.601 times 1 minus 0.601 divided by 352. Calculating all of that, we get approximately 0.037 for the standard error of differences. To compute the test statistic for the global warming study, use the difference in the observed sample proportions and the estimated standard error. The reason why you only need those two is this second parentheses, pi minus pf. Remember that this equals 0 from the null hypothesis. So we just get that fraction. So part A, to calculate the z-score using the observed difference you computed in question 3b, this would be p hat I minus p hat f, which we had above, which is 0.098. So 0.098. And then we're going to divide that by that estimated standard error that we were just given, 0.037. And if you round that quotient to 3 decimal places, you'll get 2.649. Part B, how many standard errors is the observed difference p hat I minus p hat f from the assumed mean of differences of 0? So again, our observed difference, that's 0.098. The assumed mean is 0. How many standard errors? That's exactly our z-score. This is 2.649 standard errors away. Part C, does this observed difference seem to be unusually far from the assumed mean of differences? Why or why not? Same question we've seen many times. We take a look at our z-score, and if it isn't between -2 and +2, then it is unusual. So yes, and that is because our z-score is not between -2 and 2. So it is unusually far. So now let's revisit the concept of the p-value in a hypothesis test. The p-value is the probability of observing a z-score that is at least as extreme as the test statistic, assuming the null hypothesis is true. Recall that there are 3 types of hypothesis tests. There's a left tail test, where the p-value is the area shaded in the left tail, that is to the left of our test statistic. For a right tail test, where the alternative hypothesis says p1 is greater than p2, The p-value is the area to the right of the test statistic, so it's in the right tail. And then in our case, for a two-tailed test where the alternative hypothesis has that not equal to symbol, then our p-value is twice the area to the right of a positive test statistic or twice the area to the left of a negative test statistic. For our purposes, our test statistic was our z-score 2.649. That's positive. So if we drew something related to this in number 5, we would have our normal distribution. We have a positive test statistic, 2.649. That would give us an area to the right, and if we take that area and multiply it by 2, then we get our p-value. What's related to the picture that we see is the symmetry related to the normal distribution. So the reason why we're multiplying it by 2 is because there are two tails here, but we only have to calculate that area once. So this is the area to the right of our positive test statistic. So number 6, write the p-value below. Remember that the tail's area is doubled for the p-value of a two-tailed test. So for this, let's just remember how we found those areas. We're going to multiply that area by 2, and the way that we found that area before was normal CDF. And since we have a positive test statistic, we want to think that our test statistic is the lower number, and all the way out to the right, 1E99 is the upper number. So 2.649, comma 1E99. And when you calculate that, you're going to get approximately 0.008. And that becomes our p-value. Important things to remember about the p-value. When we assume that the null hypothesis is true, we're assuming that two population proportions are equal. Then we can think of the p-value as the chance that the observed difference in sample proportions is due to chance variation. When the p-value is small enough, we no longer believe that the difference between population proportions is likely to be 0. In this case, we reject the null hypothesis that the population proportions are equal. We say that our sample data supports the alternative hypothesis. On the other hand, when the p-value is too large, we do not reject the null hypothesis. We say that our sample data do not support the alternative hypothesis. We decide whether a p-value is too large or small enough to reject the null hypothesis by comparing it to our chosen significance level, alpha. Number 7, interpret the p-value in the context of this problem. For this part, we're not looking at talking about the hypotheses yet. We are looking at this first bullet point. We're just stating what this probability means. So we can say that the probability of observing a difference in sample proportions as extreme as the one that we did, which was 0.098, the probability of observing a difference in sample proportions as extreme as that is, and this would be 0.8%, which is just taking our p-value 0.008 and converting that to a percent. Now we move on to our conclusions. It is important to explain the result of your test in a way that is easy to understand. Remember that the hypothesis testing process is not perfect, so when you explain the result of your test, make clear that there is some uncertainty. A conclusion can express support for the alternative hypothesis. The strongest support we ever give to the null hypothesis is to say that we cannot disprove it. It is always wise to indicate that the conclusion was based upon sample data. Number 8, for the global warming test, make a decision using the p-value and alpha. So first part A, what is the significance level? If you go all the way back to the beginning of this problem, you'll see that what we were given was a 1% significance level. That's on the first page of this lesson. So in this case, alpha is 1%. So we can write that as a percent, but we should also, while we are here, think of that as a decimal. So 1%, which is also equal to 0.01. Part B, use the p-value to make a decision regarding the null hypothesis. So here we had that the p-value was 0.008. We also said that that was 0.8%. And then we have that alpha is 0.01 or 1%. Whatever form you use, you can see that the p-value is definitely less than alpha. So the p-value is less than alpha. And so then in that case, if we go back to those bullet points above, when we have that the p-value is small enough, it says we reject the null hypothesis. So that's the decision that we would make with the null hypothesis. Reject the null hypothesis. While we're at it, we can also say, even though it wasn't asked in this question, the data supports the alternative. So data supports HA for alternative hypothesis. And then finally, part C. Think about the global warming surveys. State a conclusion in the context of the surveys. So here we want to put all of this together. What's our significance level? Does the data support our claim, or does the data not support our claim? Since the alternative hypothesis that we stated before was the same as our claim, that's what we wrote down at the very beginning in our first step. If the data supports the alternative hypothesis, then the data also supports the claim. So, putting this all together, we can say at a 1% significance, the data supports the claim and here we just want to write down what our claim was. That the proportion of adults in the U.S. who were concerned about the effects of global warming changed between 2010 and 2011. We were talking about in the alternative hypothesis that those two proportions would be different, which means there has to be some change between 2010 and 2011. Now we're just going to do another example just to practice this more. Next steps. Sharon P. Fowler and her colleagues at the University of Texas Health Science Center in San Antonio conducted research about people who drink diet sodas. The researchers' findings suggest that people who drink diet sodas can actually show weight gain rather than weight loss. The following simulated data are based on this diet soda study. Suppose that in a random sample of 910 people who drink a half can of diet soda per day, 239 people are obese. That is very overweight. In a random sample of 832 people who drink 1 can of regular non-diet soda per day, 252 are obese. We will test the claim that the proportion of people who are obese, the obesity proportion, is lower among people who drink a half can of diet soda per day than among people who drink 1 can of regular soda per day. We will test this claim at the 5% significance level. So first, step 1, determine the hypotheses. Part A, define P sub D to be the obesity proportion among people who drink a half can of diet soda per day. Define P sub R to be the obesity proportion among people who drink 1 can of regular soda per day. What is the null hypothesis for this test? Just like we saw before, the null hypothesis is going to have equality between these two proportions. So we can simply say P subscript D equal to P subscript R. And we can also, while we're here, state that that means that the difference PD minus PR is equal to 0. Part B, what is the alternative hypothesis? For this, we should take a look at what was written before, some key words that might be useful to find, test the claim. And this says the proportion of people who are obese is lower among people who drink a half can of diet soda per day than among people who drink 1 can of regular soda. So this is saying that the proportion for diet soda is lower than the proportion for regular soda. So that would be P sub D is lower or less than P sub R, and that means the same thing as P sub D minus P sub R is less than 0. And we should also write that this was our claim. And since we have that less than symbol in our alternative hypothesis, that means that we are going to have a left-tailed test. And we can say, since the less than symbol is in our alternative hypothesis. Number 10, step 2, collect the data. Verify that the criteria for approximate normality are met. So here we need our number of successes and failures, and we're going to organize this for the diet and the regular. And this is similar to what we did in the earlier problem, where it's just going to come from what was given to us in the data. Since they had mentioned that there was an obesity proportion, then we are considering a success as the number of people who are obese out of both of those samples. So for the first sample, 239 is our number of successes. And for the second sample, we had 252 as the number of successes. And then again, we can do some subtraction, take the total for each sample, subtract the number of successes. That's going to give you the number of failures for diet as 611, and the number of failures for regular, 580. And then since the question is the criteria for normality met? We would say yes, because we have that both of those, or all 4 of those, are greater than 10. So then part B, calculate the sample proportion of people who drink a half can of diet soda per day who are obese. That will be labeled P hat D. And then calculate the sample proportion of people who drink 1 can of regular soda per day who are obese. That's P hat R. So in this case, P hat D is 239 divided by 910, which will give us approximately 0.263. And then P hat R is 252 divided by the sample total for that, 832, and that gives us approximately 0.303. And then part C, compute the difference in the observed sample proportions. That is just going to be 0.263, that's P hat D, minus 0.303. And when we subtract that, we get negative 0.040. Keep in mind that it is okay to get negatives since you are finding difference here. Step 3, assess the evidence. Part A, use technology to calculate P bar, and then the standard error, and then finally the test statistic. So P bar, again, this is where we add the successes and then divide by the total of the sample sizes. So this will be 239 plus 252 in the numerator divided by 910 plus 832, and that will end up being approximately 0.282. And then the standard error, notice they abbreviate that as just capital SE. So if we plug everything into that formula, we'd have square root. Underneath P bar, that's 0.282, times 1 minus P bar, that is 0.718, divided by the first sample size, which is 910, and then still under the square root, another fraction, again with 0.282 times 0.718, but then we divide this time by the second sample size, that's 832. And if you calculate all of that, you're going to get approximately 0.022. And then putting all of this together into our z-score, remember from what we saw before, this just ends up being the difference in sample proportions divided by our standard error. So we have negative 0.040 divided by 0.022. And that gives us approximately negative 1.818. And that becomes our z-score. So then part B, how many standard errors is the difference P hat D minus P hat R from the assumed mean of differences? Here again, we're just using our z-score to interpret, but this time with that negative, this is indicating that we have the difference being below the assumed mean. So it is 1.818 standard errors below the mean. Part C, does the test statistics seem to support the claim that the obesity proportion is lower for people who drink a half can of diet soda per day? Why and how do you know? This is really just asking if we have an unusual z-score. So already right here, we would say no, since the z-score is between -2 and 2. Part D, use the test statistic to determine the p-value. Sketch the normal distribution, identify the position of the test statistic, and shade the area that corresponds to the p-value. So again, we have just our normal distribution. Our test statistic is negative, so that's on the left side, negative 1.818. The p-value is just the area that's to the left, because we only have a one-tailed test. So our p-value, we're going to use normal CDF. And since we have a left-tailed test, our lower z-score is negative 1E99, and our upper z-score is negative 1.818. And if we use our calculator for that, we're going to end up getting approximately 0.034. Part E, interpret the p-value in the context of this problem. Again, this is interpreting the probability. So we can say that the probability of observing a difference in sample proportions as extreme as the one that we did, which was negative 0.040, under the assumption that, and here we're stating our null hypothesis, PD minus PR, which means our difference should be 0. The probability of that is our p-value, which is 3.4%. So now number 12, state a conclusion. Part A says, what is the significance level? That's 5%, which is the same thing as 0.05. Part B, do you reject or fail to reject the null hypothesis? Again, our p-value is 0.034 and alpha is 0.05. We again have that the p-value is less than alpha, and so then this gives us a conclusion of reject the null hypothesis. Finally, part C. This hypothesis test focused on the relationship between obesity and whether or not people drink diet soda or regular soda. Write a conclusion to this hypothesis test. In your conclusion, explain what you believe the data suggests about this relationship. So again, similar to what we saw before, we've rejected the null hypothesis, which means that the data supports the alternative hypothesis. Since the alternative hypothesis is our claim, it also means that the data supports the claim. So we would say, what significance at the 5% level of significance the data supports the claim. And here we're just rewriting what the claim was. Supports the claim that the proportion of people who are obese is lower among people who drink a half can of diet soda than among people who drink 1 can of regular soda. To further understand a little bit of what we just saw with this, we're going to take this time to calculate a confidence interval. Number 13, to finish this whole problem, use technology to compute a 90% confidence interval for the difference in population proportions, PD minus PR. The critical value in part A for the 90% level of significance is Z sub C equal to 1.645. Use technology to compute the margin of error for the estimate. So here we would take our Z-score, 1.645. This is the one that's given for the level of confidence. And then multiply by this estimated standard error, the square root of p hat d times 1 minus p hat d, all divided by nd, plus p hat r times 1 minus p hat r, all divided by nr. So putting all of that into the formula. P hat d, we said before, was 0.263. So 0.263 times 1 minus 0.263, all divided by the first sample size, 910, plus, and then p hat r we said was 0.303. We'll multiply that times 1 minus 0.303, and then divide by the second sample size, which was 832. And then multiplying all of that together, we're going to get approximately 0.036. So then part B says, what is the confidence interval for the difference in proportions PD minus PR. Here we would just take our difference, P hat D minus P hat R, and then subtract the margin of error, and then take P hat D minus P hat R and add the margin of error. We said that that difference was already negative 0.040. And then that gives us a confidence interval of negative 0.076, comma, negative 0.004. So then we're just going to answer a couple questions based on this confidence interval. Part A, can we conclude which population has a higher obesity rate? That is, can we conclude that the people who drink a half can of diet soda have a higher obesity rate? Or can we conclude that people who drink 1 can of regular soda have a higher obesity rate? Explain your answer. What we can notice in our confidence interval is that both numbers are negative. Both numbers in the confidence interval, I'm just abbreviating that as CI, are negative. So that means that estimates for the difference PD minus PR are negative. The only way that you get a negative from a difference is if the second number must be larger. Which also means that the first number must be smaller. So this is telling us that the proportion is less for those that drink diet soda. So when it says which one can we conclude have a higher obesity rate, it must be that those who drink 1 can of regular soda. And then finally, part B, how does our conclusion relate to the hypothesis test? Explain your answer by thinking about the values in the interval. So again, our conclusions agree because we said the same thing for both. With our hypothesis test, we said that those who drink a half can of diet soda, the obesity rate is lower. We said the exact same thing here. So they agree.